Hi everyone, I'm Takafumi Kamizuka from University of Tokyo in Japan. At first, I'd like to thank the organizers to have this nice workshop and give me this opportunity to talk. And thank you very much. And the title of my talk is shown here, Challenging the Difficulties in Ground-Based MidInfrared Observations, the case of Takafumi Kamizuka. I hope this is related to the assigned topic, high background. One of the high topics, but I couldn't understand what the topic means. So I asked Inami-san for it. And she said high background includes observations of infrared bright sources and treatment of high background in ground-based observations. And I can really select that topic. So in this talk, I'd like to talk about our technical challenges to the knowing atmospheric high background for realizing MIR monitoring bright sources. Okay, as many speakers already mentioned, the JWST is now successfully flowing in space and preparing for observations. And it is undoubted that many unprecedented data will come up in near future. The best thing about the JWST has both high sensitivity and high resolution. And the great sensitivity is achievable only in space. In such an era of the JWST, the mission of Bandbased observatories is to advance science with complementing the JWST. For example, the 30-meter class telescopes can achieve higher spatial resolution than the JWST, and smaller telescopes can be used for survey-like observations and monitoring observations, which are too costly for the JWST. So we should continue to advance ground-based mid-infrared observations, even in the air. But there is a nuisance here, atmosphere. I think there are two annoying points of the atmosphere. One is a bright variable emission. The brightness is orders of magnitude greater than the astronomical objects. In addition, that varies in time with a time scale less than 1 second. We needed to accurately remove them for observations. The next point is the varying absorption. We have to correct for it to measure the brightness or spectrum of object, and miscorrection will lead to errors, and which makes time domain astronomy difficult. So we want to overcome these difficulties, and we are make challenges in development of our instrument, MIZuku. At first, I'd like to introduce our telescope and instrument. Tau is the name of an observatory we are now building in Zurich. The location is shown here, and that is the top of a mountain called Seochakanantou, close to the Auma site. The altitude is 5,600 meters, and we will put a 6.5 meter telescope here. And as I will explain in the next slide, the site is very ideal for mid-infrared observations. So the telescope will be a relatively large university's telescope at a very nice site for mid-infrared observation. The most significant point is the atmospheric transmittance, because the site is located at high altitude in desert. So the water vapor in the atmosphere will be suppressed, and a low amount of the water vapor gives a good transmittance. And this figure shows the calculated atmospheric transmittance compared to the other sites. The green one is Subaru site, and red one is BLT site, and the blue one is our Tau site. We can see that near-infrared atmospheric windows become continuous, and some new atmospheric windows emerge around 2.7 microns here and 30 to 40 microns here. In addition, the Q-band transmittance is also improved. Based on this, we can say that the site is ideal for MIR observation. Just a moment, please. No. So it's a heavy slides. Just a moment, please. Yes. And now we are building the observatory. Unfortunately, the construction was interrupted by COVID-19, but we have resumed the construction now. This picture shows the many parts waiting at the foot of the mountain to be used for construction. And at the summit, the telescope pier has been established here, and the telescope will be built on this pier. In addition, large parts of the telescope and mirror coating system are also transported to the mountain skirts. So we hope to finish the construction and start observations in next year. This is the current status of the observatory. And next, let's move on to instrument. Here is a 3D model of the Tau telescope. And there are two main instruments attached to the Nasmith foci of the Tau telescope, here and here. One is the near-infrared instrument named SWIMS. And the other one is MIMIZUKU. This is a mid-infrared instrument. I will continue. I will introduce this instrument from now. Now, MIMIZUKU is an abbreviation of this very long name, and the appearance is shown here. The size is about 2 meters, and the weight is about 2.5 tons. The main features are shown here. The first feature is a wide wavelength coverage. And this instrument covers 2 to 38 microns with 3 optical channels named NIR channel, MIRS channel, and MIRL channel. MIRS means short wavelength mid-infrared, and MIRL means long wavelength mid-infrared. And the NIR channel covers 2 to 5.3 microns with an H1 RG array. And the MIRS channel has an Aquarius array to cover the wavelength range from 7 to 26 microns. And the MIRL channel covers 30 micron band with antimonide silicon array. And each channel allows us to perform imaging and low resolution spectroscopic observations. And the second feature is the good spatial resolution. Because the optics is designed to achieve the diffraction limit resolution, the spatial resolution is determined by seeing effect and the diffraction limit of the telescope. The expected values are shown here, ranging from 0.5 to 1.2 arcsec, depending on the wavelength. And the development had started in 2009, and the MIRS channel achieved the first light in 2018 at the Tau telescope. I will show some results obtained in the first light observations. Here is the result of imaging tests of the MIRS channel. These are the images of point sources and their radial profiles. The top panels are the N-band data, and bottom ones are Q-band data. By analyzing these data, we confirm the diffraction limit spatial resolution as shown here, 0.4 arcsec in N-band and 0.6 arcsec in Q-band. And we also evaluated the system efficiency, shown here, 21% for N-band and 5% for Q-band. The value for N-band is expected from the design, but for Q-band, this was slightly lower than expected, but still acceptable, I think. And next one is spectroscopic results. The raw images are shown in the left panels, and the middle ones are background subtracted images, and the right ones are extracted spectra. And the top panel shows the N-band data, and bottom ones are Q-band data. And by analyzing by examining the atmospheric absorptions in the extracted spectra, we evaluated the wavelength coverages and resolutions as shown in this table. It was found that the N-band mode covers 7 to 13.5 microns with a resolution of 170. And the Q-band covers 16.5 to 26 microns with a resolution of 110. These values are expected from design. Although the Q-band efficiency was slightly lower than expected, but the first flight observations show that the MIRS channel is working almost as designed. And after the observations at Subaru telescope, we returned the MIMIZUKU to Japan, and we are now developing the other channels, NIR and MIRL channels. This is our current status of MIMIZUKU. And after completing all channels, we can utilize them for a variety of science cases. Each channel has characteristic observables and related science cases. I show some example here. In the NIR channel, it might be possible to observe 2.7 micron feature from hydrosilicates on asteroids. And survey studies of them would be useful to investigate the origin of water or thermal history of asteroids. In the MIRS channel, we can observe a variety of dust features and determine the temperature of warm dust. And the monitoring studies of these things are expected to unveil the dust formation process and evolved stars. The high-resolution imaging in the MIRS channel would reveal the distribution of cold dust, which is related to the study on the mass ejection history of evolved stars. From now, I will talk about 3 technical challenges to realize these studies. The first one is the removal of background emission. As already mentioned by some speakers yesterday, we usually use a method called chopping for removing the high background emission. In this method, we observe an object with frequently switching the observing field. As illustrated in this picture, we observe this object in fields A and B and take image in each field. In the raw images, the object is obscured by the high background emission, like these pictures. The objects are faintly seen here and here. And if we subtract each other, we obtain an image with the background subtracted, and we can see the object here and here. And if we can switch the field and take images before the background changes, the background emission is successfully subtracted. This is a chopping method. And conventionally, the beam switching has been achieved by frequently tilting the telescope secondary mirror, as shown in this figure. The upper part is a telescope, and the bottom part is instrument. And these lines show the optical path in observing. By tilting the secondary mirror of the telescope, the observing field is switched like this. We call this method secondary mirror chopping. But now the method is evolving into another method called cold chopping. This is illustrated in the right part. In this method, we place a cold movable mirror at the place conjugate with a secondary mirror inside the instrument. And by tilting this mirror, the observing field is switched, as in the secondary mirror chopping. The merit of this method is that the moving part can be small. This part is very smaller than the telescope secondary mirror. This is very important in the era of large telescopes because the secondary mirrors of Earth telescopes are very big. It is too big to achieve the frequent fast motion. Therefore, this method is a key technology for next generation MidInfrared observations. However, we have to develop this movable mirror system operating in cryogenic temperatures, which is called cold chopper. In the development of MIMIZuku, we are developing a cold chopper because the secondary mirror of the Tau telescope cannot move so quickly. And here is a prototype of our cold chopper system. The body is made of aluminum alloy, and 2 pairs of flexural pivots inserted here, 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 and here. And they allow 2D rotation of the central body. The rotational axis is shown these dotted lines. And by making this surface a mirror surface, this system will be a cold chopper. And our requirements are listed here. The operational temperature is less than 30 Kelvin. The chopping frequency should be greater than 2 Hz. And the chop slow should be greater than 30 arcsec in on sky. And we also require short traveling time and good stability and low heat dissipation. And recently, we successfully achieved the cryogenic operation of this prototype model. And here is an example of the result of the cryogenic test. These panels show the movement of the chopper mirror. The horizontal axis shows the time since the first edge of the motion, and the vertical axis shows the mirror angle. We can see that the mirror is moved like a square wave with a frequency of 2 Hz. The amplitude corresponds to a chop slow of 60 arcsec on sky. And the right panel shows a close-up of this region. And this red dashed line shows a steady state level, and the dotted lines show the allowance range from the stability requirement. And we can see that the traveling time is less than 15 milliseconds, and the fluctuation after that is almost within this allowance range. In addition, the heat dissipation was found to be very small, around 5 milliwatt. These results show that our chopper system can achieve requirements, and therefore we are preparing for installing this system in MIMIZuku. And this experience will be useful for next generation MIR instruments like TMT MICHI. Here is a second challenge. This is related to the atmospheric correction. As you all know, in ground-based observations, we need to compare the signals of a target and a reference object to correct for the atmospheric absorption. MIMIZuku has a system for assisting the correction that is called field stacker. And the system is shown here. The system is placed on the focal plane of MIMIZuku around here, and it consists of 3 movable mirrors, this one and this one and this one. And the 2 mirrors here and here pick off light from two fields. And then another mirror combines them into one beam and feeds it into the cold optics of the MIMIZuku. And this function allows us to observe the target and the reference star, target and reference star simultaneously, even if they are separated with more than 2 arc minutes. Such simultaneous observations improve the accuracy of the atmospheric correction, even if the absorption shows the time variability. And the real view of this field stacker system is like this. The 3 mirrors are shown here and here and here. And here is the result of field stacker imaging tests obtained at Subaru. This is a chop subtracted image, and we can see the combined two observing fields in right and left side. And in each field, one object is imaged in positive and negative. And this is due to the chopping subtraction. And if we measure their counts, we obtain a time series data as shown here. The four colors correspond to these four images. And in this plot, the photometric count varies with a peak to valley value of about 10%. This is due to the weather condition. If we observe these objects separately in different times, a correction error of up to 10% may occur. Even in such bad condition, since we have simultaneous data and the fluctuation occurs in the same manner on both objects, so we can eliminate the fluctuation by taking their ratio. The result is shown here. And we can see that there is only a small fluctuation. And by taking the average of this ratio, we can achieve a relative photometric accuracy of less than 1%. This means that the simultaneous observation with field stopper can improve the photometric accuracy. And this system also works well on spectroscopic observations. This panel shows an image taken in the Q-band spectroscopic mode, and the objects in field 1 and 2 are successfully observed simultaneously. The extracted spectra are shown here. Left panel shows the N-band data, and right panels are Q-band data. And top two panels are the raw spectra of the two sources. And in the spectra, we can see atmospheric absorptions. Here is the ozone absorption, and in the Q-band spectra, and water vapor absorption makes a very wavy spectra like this. And by taking their ratio, the absorption bands are compensated, and we can get a smooth spectra as shown in this bottom panel. The compensation succeeded even in the Q-band. This result suggests that the field stack observation enables us to perform Q-band spectroscopy even in ground-based observations. Okay, this is the last one. Okay, and this is the last one. This is related to the flood collection. This is not related to the atmospheric problem, but important for improving calibration accuracy required for monitoring studies. For flood fielding, we must consider both optical flood and detector flood, and we must also take care of the nonlinear behavior of the detector response. This picture illustrates the nonlinear response of the detector. Horizontal axis is the integrated photons, and the vertical axis shows the output signals. The detector response is shown in this red solid line. In ground-based observations, we usually use a limited region, as shown in this orange square, due to the high background emission. In this region, the detector flood is determined by the pixel variety of the local gradient, shown on this green line. On the other hand, in our community, we usually use the normalized image created by subtracted dark frame from sky frame. This corresponds to this gray light. This is named global differential. As seen in the picture, the global differential can differ from the local gradient due to the nonlinearity. For determining the local gradient, we are developing a new method to measure the response by varying the incoming photon rate, like this white point. And we made two flat frames with MIMIZUKU with two different methods. The flat frames are shown here, and the left one is made from the global differential, and the right one is created from the local gradient. And the bottom panel shows the images collected with the two flat frames. As a result, we confirm that the left edge of each reader stripe cannot be corrected properly with the global differential plot. We are now checking the cause of this phenomenon in detail, but we think we should use the local gradient plot for accurate plot correction. And now we are developing an onboard calibration unit for making the local gradient plot. I'd like to explain this unit, but since I do not have enough time, so I will skip this slide. Finally, I'd like to summarize my talk. In this era, ground-based observations still have missions to advance science with the JWST. For that purpose, monitoring and surveying observations with smaller telescopes and high-resolution observations with 30-meter telescopes are important. And for supporting such observations, technical developments are still needed. In the development of MIMIZuku, we are making such challenges to overcome difficulties in ground-based MIR observation. We are developing a code chopper for good removal of high background and field stacker system for accurate atmospheric Doppler pressure, and onboard calibration unit for good flat correction. And by using these systems, we would like to start surveying or monitoring observations in near future. I hope to 2023. That's all. Thank you very much.
Thank you very much, Kamizuka. That's a very nice talk, and it's great to see MIZuku is getting together. It's getting exciting, more and more exciting. So we have a few questions. All right, so let's start. First question is from Els. I may have missed it, but I saw in one of the earlier slides, it was mentioned that the spectral resolution was 100 to 600, while later on the slide showing the first result for the MidInfrared, it was mentioned that R is around 100. Is R 600 also possible in MidInfrared, or is it just for near-infrared?
Not possible. The 600 is available only in NIR channel, and 60 is available only in MIL channel.
Okay, I hope that answered the questions. And I see Eric has hand raised, so maybe Eric, you can go for your question.
Hello, nice talk. Thanks. The field stacker is a very nice idea to monitor any variation. I just wonder about the availability of standard stars or simply stars that you can observe. I suppose that there's a maximum offset that in which you can search for your standard star. So can you remind me what is the maximum offset standard star, and did you check if for any object in the sky there would be such a standard star that could be observed?
Yeah, that's a very important question. And this mechanism is designed to observe two objects separated within 25 arc minutes. And but now this distance is limited by the field of view size of the telescope, and that is about 20 arc minutes now. So the availability is slightly decreased now. But we had checked the availability, and there are many infrared sources in the midplane and galactic plane. So and the density is very high, so we can observe a reference object with a possibility of about 60% around. So it depends on the wavelength range in band or Cuba.
Thanks.
Okay, thank you.
Okay, I think we can do one more question at least on Slack. Thank you for a very nice talk. Can you say a bit more about code chopping for performance for MIMIZuku? In particular, Metis would be quite interested to know if you see any residual from inhomogeneity or thermal gradients in the entrance window. That is a question from Leo.
Yes. more detail. Yes, the METIS also has a very nice this kind of code chopper, and but we cannot compare the properties directly because the optical system is different. But for our system, the nice point is this heat dissipation. I think the METIS chopper is creates about 100 milliwatt heat dissipation, but our chopper only creates about 5 milliwatt. This is a very nice point for our system.
If I may
yep.
just specify, I mean, Hane read the question, but just the specific question would be if you see residuals from the fact that you're chopping behind the entrance window, because that's a worry that we have in METIS, where we plan to do the same, as you know, and we're wondering whether any inhomogeneities or thermal gradients in the entrance window could lead to residuals when doing the chop subtraction. Can you comment on that? Have you seen that in MIMIZUKU?
Because our system is now outside of the MIMIZUKU, and we do not have results in MIMIZUKU, so we don't have such information about that. But we are now preparing for installing this system in MIMIZUKU. And in such tests, we will confirm such, we may confirm such problem.
I see, thank you.